Welcome back to the deep dive. Today, we are looking under the hood of an app that I can almost guarantee is running on your computer or phone right now.
Oh, absolutely.
But we aren't just talking about it because it's popular. We're talking about it because, architecturally speaking, it is a monster.
It really is. It's a monster of performance
Yeah.
in, I mean, the absolute best way.
We're talking about Discord. Now, usually when you and I think of Discord, we just think, oh, that's where I chat with my gaming buddies or, community management.
Right.
But when you actually peel back the UI and look at the engineering required to keep that thing alive, it is staggering.
It's the scale that gets you. I mean, we aren't talking about a standard website where you load a page and you're done.
Yeah.
We're talking about tens of millions of concurrent connections. Real time. Low latency.
And it's not just simple text, right? It's not just sending hello world.
No, not at all. It's heavy data. You have member lists updating in real time for servers that might have hundreds of thousands of people.
Hundreds of thousands.
You have presence updates, who is playing what, who is online, who is typing, and this is all happening simultaneously millions of times a second.
And that is the mission for this deep dive. We have a stack of sources here, including a dense technical case study from Discord's own engineering team and a comparative analysis of microservices versus the Erlang OTP philosophy. We are going to unpack how they pull this off. Because, spoiler alert, they aren't doing what everyone else is doing.
That's the key. If you followed the standard Silicon Valley playbook, you'd grab Kubernetes, spin up a bunch of, standard microservices, and call it a day.
Right.
Discord took a contrarian path.
They combine two technologies that, on paper, look like they have nothing in common. You have Elixir, which we're calling the system thinker, and then you have Rust, which is just pure raw performance.
It's a hybrid architecture.
Yeah.
And frankly, it solves problems that the standard industry approach can't.
Okay, so let's unpack this. If we are building this monster, we have to start with the front door, the entry point.
The gateway.
In Discord's world, the gateway is handled by Elixir. Now, for the uninitiated, Elixir runs on the Beam VM, which comes from the world of Erlang. And Erlang is, well, it's old school. It was built for telecom systems, right?
Exactly. It was built to run telephone switches. And if you think about a telephone switch, it has to handle thousands of calls at once, and it absolutely cannot go down.
Can't fail.
That is Elixir's DNA. Its sole purpose in Discord's architecture is to hold the door open.
So it's the doorman.
It's the ultimate doorman.
Yeah.
Its only job is to maintain those millions and millions of WebSocket connections.
But why Elixir? I mean, why not Java or Node.js? Everyone uses Node for real-time stuff.
It comes down to how they handle memory and threads. In many traditional languages, a thread is heavy. It takes up a significant chunk of memory just to exist.
Okay.
But Elixir uses the Erlang process model.
Process sounds heavy, though, like an operating system process.
In this context, it's the complete opposite. These are lightweight processes. We are talking about maybe 2 kilobytes of RAM per user.
2 kilobytes? That is microscopic.
It is. So you can pack millions of them onto a single server. But the real magic isn't just the size, it's the isolation. We call this fault isolation.
Explain that, because usually, if a process crashes, it's bad news.
In a traditional app, if one thread goes rogue and crashes, it can take down the whole application. It's like a domino effect.
Right.
But in Elixir, every user is their own tiny, isolated island.
So if I send a malformed packet, or my connection just glitches out.
Your tiny process crashes and restarts. That's it. My connection running right next to yours on the same chip doesn't even notice.
Wait, hold on. Let it crash is a famous slogan in the Erlang world. But as a user or, a business owner, that sounds terrible. I don't want things crashing. Why is Discord okay with this?
It sounds counterintuitive, doesn't it?
Yeah.
We are taught in Computer Science 101 to catch errors, handle them, suppress them. But Erlang says, no. If the state is corrupted, kill it. It's safer to restart a fresh, clean process than to try and limp along with a buggy one.
It's the have you tried turning it off and on again method, but applied continuously thousands of times a second at a microscopic level.
Precisely. And because it happens so fast, the user never even notices.
The numbers in the engineering blog really drive this home. They mentioned a single server running Elixir can handle 1.2 million concurrent WebSocket connections.
Which is just absurd.
And this is the part that blew my mind, using just 12 CPU cores.
That is the efficiency of the Beam VM. I mean, if you tried to do that with a standard thread-based architecture in Java, you'd likely need a whole rack of servers, not just 12 cores.
Okay, so Elixir is the perfect doorman. It handles the crowd, keeps the lines moving, makes sure no one steps on anyone else's toes. But looking at the case study, Elixir isn't perfect at everything.
No tool is.
We get to part 2 of our story, the muscle. Because eventually you have to do something with all that data coming in. And it turns out Elixir is a bit of a slow reader.
It's not just that it's a slow reader. It has a fundamental structural issue with how it handles large lists of data.
So let's look at the specific problem Discord hit. The member list.
Right. Imagine a gaming server with 500,000 members. You have to sort them by role, by status, who's online, who's playing League of Legends, who's listening to Spotify.
And that list changes every single second.
Every second. And Elixir choked on this.
It struggled.
Yeah. And to understand why, we had to get a little technical about data structures. Elixir is a functional language. It uses linked lists.
Okay, picture that for me. What's the difference between a linked list and, say, a standard array?
Imagine you have a list of names. In a language like C or Rust, that list is like a spreadsheet or an index card box. If you want the 5,000th name, the computer knows exactly where it is in memory. It jumps straight there. Boom.
Instant access.
Exactly. But linked list, it's like a treasure hunt. The first name holds a clue that points to the second name. The second name points to the third.
Oh, I see where this is going.
If you want to find the 5,000th person, you have to start at number 1 and follow the trail all the way down. You have to traverse the whole chain.
That sounds exhausting for the CPU.
It is, and it gets worse. Elixir data is immutable. That means you can't change it. You can't just cross out a name and write a new one.
So if one person goes offline,
You basically have to copy the entire list to create a new version with that one tiny change.
you're tearing up the treasure map and drawing a whole new one every time someone logs off.
Exactly. For a small list, no problem. For 500,000 people changing status constantly, it burns CPU cycles like crazy.
So naturally, they needed a different tool. And initially, they tried Go.
Yes, Go is fantastic. It's fast, it's modern. They wrote the read states service, which tracks what messages you've read, in Go.
And it worked until it didn't.
It worked great most of the time. But every few minutes, they would see these massive latency spikes. We're talking 500 milliseconds or more.
Half a second. In the gaming world, that is an eternity. That's, I just died in the game because of lag territory.
It's a rage quit moment. And the culprit was the garbage collector.
The janitor.
Right. Go is a managed language. It has a system that cleans up memory in the background. But when you have that much data, the janitor sometimes has to say, stop. Everyone stop working. I need to clean this mess up.
That's the stop the world pause.
Exactly. For a split second, the entire service just freezes.
So they couldn't stay with Go. They made the move to Rust. Now, Rust has a reputation. It's the scary one. It's hard to learn.
It is the muscle.
Yeah.
But here's the key difference. Rust doesn't have a garbage collector. There is no janitor.
So who cleans up the mess?
You do. Or rather, the compiler forces you to design your code so that the mess cleans itself up instantly. It uses what we call zero-cost abstractions.
Which
Means the code you write compiles down to machine code that is as fast as C++ bay. There's no overhead, no pauses. It's just raw speed.
And the result?
Night and day. The latency dropped from those 500-meter spikes down to like 10 to 50 milliseconds, a 10x improvement.
Wow. And memory.
The memberless service went from using 8 gigabytes of RAM in Go down to 1.5 gigabytes in Rust.
That is massive efficiency. So we have Elixir handling the connections, the doorman. We have Rust doing the heavy data processing, the muscle. But here's where it gets risky. How do you connect them?
This is the critical piece.
Yeah.
Because you can technically embed Rust code directly inside Elixir. There's a feature called NIF's native implemented functions.
It sounds convenient. Just run the fast code inside the smart code.
It is convenient, but it's so dangerous. It's like inviting the muscle directly into the doorman's booth.
Yeah.
If the muscle trips and falls.
It crushes the doorman.
Exactly. NIFs run in the same memory space. If the Rust code crashes or has a memory leak, it takes down the entire Erlang VM. The node dies. All those millions of connections drop instantly.
So the fault isolation we loved so much about Elixir gets completely bypassed.
Right. You lose your entire safety net. So Discord needed a buffer, a firewall, and that brings us to gRPC.
They separated them into entirely different microservices.
All right. They put the Rust code in its own service, on its own server or pod. Elixir talks to it over the network using gRPC.
So now, if the Rust service crashes,
Elixir just gets an error message. Hey, the request failed. The doorman is fine. The user stays connected. The app doesn't close.
and reading through the sources, they didn't just stop at separating them. They built these incredible defense mechanisms. It feels like they're paranoid about their own success.
When you operate at that scale, you have to be paranoid. They have mechanisms to prevent Death by success.
One of my favorites was the bulkhead pattern. It sounds nautical.
It is. Think of the Titanic.
Mm.
Ideally, you have watertight compartments. If the hull is breached in one spot, only that compartment floods. The ship stays afloat.
And Discord does this with their connection pools.
Exactly. They separate the critical tasks from the non-critical. Sending a message, that's critical.
Right.
Loading the member list, that's nice to have, but not life or death.
So they ration the resources.
Right. They might allocate 80% of their connections to sending messages and only 20% to member lists. So if the member list service completely clogs up and fails, that compartment floods. But the chat.
The chat keeps working. That is brilliant engineering. It prioritizes the core user experience above everything else.
It ensures that a feature failure doesn't become a platform failure.
So we've seen the specific architecture, Elixir, Rust, gRPC. But I want to zoom out now, because this connects to a much larger philosophical battle in the tech world. We have the Discord model, this hybrid, and then we have the industry standard. Kubernetes and microservices for everything.
The microservices versus monolith debate, or in this case, microservices versus the Erlang way.
The sources refer to something called the network tax. That feels like a perfect bridge here. What is the network tax?
Think about a standard microservices architecture. You have service A calling service B calling service C.
Okay.
Every time A talks to B, it has to package up the data, serialize it, send it over the wire, go through a load balancer, get unpacked, and processed.
That sounds like a lot of bureaucracy.
It is. It costs CPU and it costs time. In a standard setup, that hop might add 20 milliseconds of latency. That's the tax you pay for splitting things up.
But Discord avoids this.
Internally, in Elixir, yes. Because Elixir processes live in the same memory, message passing is instant. It's not mailing a letter, it's passing a note to the person sitting right next to you.
Oh, wow.
The latency is practically zero.
So they only pay the tax when they absolutely have to when they go out to Rust.
Exactly. They accept the tax for the Rust service because the performance gain of Rust is worth the cost of the network hop.
Okay, so let's pause. The expert speaker voice in my head, that's you, is making a very compelling case. This sounds technically superior, lower latency, lower hardware costs. I mean, saving 60% on infrastructure is huge, and better stability.
It is technically superior for this specific type of real-time problem, yes.
So here is the uncomfortable truth of the tech industry. If this architecture is so good, why isn't everyone doing it? Why are Google, Amazon, and Facebook still rolling out massive Kubernetes clusters with Java and Go microservices?
Right.
Why aren't they rewriting everything in Elixir tomorrow?
2 words, hiring and inertia.
Let's talk about hiring. Is it really that hard to find the wizards?
It is incredibly hard. Elixir and Erlang are niche languages. If you post a job opening for a Java developer, you get a line around the block. There are millions of them.
And if you post for an Elixir expert,
You might get 3 people. And they probably already work for Discord, WhatsApp, or Ericsson.
so you're not just betting on the tech, you're betting on your ability to build a team that speaks a very rare language.
Precisely. And that connects to the organizational argument.
Oh,
We
good.
talked about the network tax on computers. But microservices solve a different kind of tax, the communication tax on humans.
Explain that.
Imagine a company with 10,000 engineers. Trying to get 10,000 people to work on a single code base, even a well-structured one like Erlang, is a nightmare.
Oh, yeah.
You have merge conflicts, you have coordination meetings that last forever.
So microservices aren't just about code, they're about org charts.
Yes. Microservices allow Team A to write in, go and deploy on Tuesday, and they don't have to say a word to Team B, who writes in Java and deploys on Wednesday. It decouples the people.
It's easier to scale the teams even if the software is less efficient.
Exactly. You are paying a network tax with your computers to avoid a communication tax with your humans.
We pay for our organizational complexity with electricity bills.
That is a great way to put it. Discord refused to pay that bill because they couldn't afford to. They were a startup. They needed the efficiency. But a company with infinite cash, they'll just buy more servers.
There was also a physical risk mentioned in the comparison, the burning building scenario.
Right. This is the argument against the stateful model of Erlang. If you have a massive Erlang server holding the open connections for 2 million users in its RAM, and that physical server burns down,
You lose 2 million connections instantly.
the blast radius is huge. Kubernetes and standard microservices naturally spread things out. They assume the hardware is unreliable. They assume the server will burn down.
So sometimes the worst technical solution is the safer business bet.
Often, yes. For a big tech company, buying 500 extra servers to cover the inefficiency of standard microservices is actually cheaper than the time, risk, and training required to adopt a complex, stateful architecture like Discord's.
It's a trade-off, efficiency versus convenience.
Always.
So let's wrap this up. We've geeked out on linked lists. We've bashed garbage collectors. What are the big takeaways for you?
First, Discord proves that right tool for the right job isn't just a cliche. They used Elixir for connections because it's the best at concurrency. They used Rust for speed because it's the best at math.
Right.
And they used gRPC to glue them together safely. They didn't settle for good enough.
And the results speak for themselves. Massive cost savings, incredible stability. But it also highlights that there is no one architecture to rule them all.
Right. If you are building a standard e-commerce site, please just use standard microservices. Do not try to build a distributed Erlang system for a shopping cart.
Unless you expect 5 million people to put an item in the cart at the exact same second.
Then maybe give Elixir a call.
I want to leave the listener with a final thought here. It feels like we are at a crossroads. Computers are getting faster, the cloud is getting cheaper, but software seems to be getting bloated. We add layers and layers of abstraction, Kubernetes, service meshes, sidecars.
We prioritize developer convenience over machine efficiency. We optimize for the engineer, not the electron.
Exactly. So here's the question. As we hit the limits of Moore's law, or as energy costs for data centers rise, will we see a swing back? Will more companies be forced to abandon the easy path of standard microservices and look back at the ancient wisdom of Erlang and high-efficiency architectures? Or will we just keep buying more servers to mask the bloat?
That is the billion-dollar question, and looking at Discord, the answer for the future might be hybrid.
Something to think about the next time you hop into a voice channel and it connects instantly. Thanks for listening to this deep dive.
See you next time.